Welcome everyone to today's video. So we are going to start with Archimedes principle today. So it's a pretty interesting idea in fluid mechanics. It's one of those ideas which came before Newton's laws. So it carries significance in that way. And even today, a lot of questions are asked on the basis of this idea. So the idea goes something like this: we have a body. That body is basically placed inside a fluid. So, first of all, what was a fluid, which we have been talking about? Fluid is something where the interatomic forces are relatively weaker in comparison to solids, and the interatomic distance is higher. So, both air and water, or air and or any other liquid, we say they are fluids. So when we immerse something inside a liquid like water, it is displacing water. So Archimedes' principle says that ki whatever force is exerted by that liquid on that body, that is equal to the weight of the fluid or weight of the liquid displaced by that body. So how does that happen? So basically, it's pretty easy to understand in way if we think that ki, let's say if I have a container and this is the liquid which I was talking about. So what was Archimedes' principle? Archimedes' principle was that ki, if an object is placed like this, the upthrust exerted by the fluid surrounding that object in obviously this direction, upward direction, is equal to the weight of the fluid displaced by the body. So, one way with which we can understand this idea is that let's say if the object is not there, simply. So, if there is a in place of object, I simply have a liquid here in the shaded region. Then, what is the force exerted by the surrounding liquid on the shaded part? It will be equal to the weight of the liquid, right? Because this liquid, which is basically in place of the object here, it is completely balanced here. So, what is the force exerted by the surrounding forces on this particular shaded region? It is only the weight of the shaded region. It would act just like a normal reaction. Like normal reaction is acting on some body kept on a surface. Instead, here the surface is of this whole liquid, and it is exerting a weight equal to the weight of the liquid. So now, if the upward force acting on this body is instead acting on this is acting on this body, then the surrounding fluid will see this body just like a liquid only. It will see that this object is nothing but what I was seeing earlier. It was a liquid earlier. So it will exert that force only on this object in the upward direction. I'll explain that once more so that it is clear. Basically, this surrounding fluid will see that uh, it does not care what resides within the surface, right? Whatever the surface we have drawn in the shaded region, whatever object is there or liquid is there, that is not cared for by this liquid. The surrounding liquid only cares that I have to balance the weight of this fluid or this liquid which is in this region. Now, if there is an object in this place, or if that liquid only was at that place, the surrounding liquid will exert the same force only on this object in upward direction. So that is what Archimedes principle is. It says that the weight or this upward force what upthrust force acting on this object F, let's say, and let us label it as FB is equal to volume of the fluid displaced, let's say V rho G. So V is the volume of the fluid displaced. Rho is the density of the fluid, and G is acceleration due to gravity. So this is what the formula for Archimedes principle is. So next, we want to apply this idea in some situation, right? We want to learn, okay, how to apply this concept. So let's say I have some cubical block. So this cubical block is placed in the liquid like this. Now the side of the block is, let's say, some 10 centimeter. We know that some x height of the block is immersed in this liquid. So if we know that the side of the block is 10 centimeter, the density of the fluid is 10 to the power 3 kg per meter cube. This is the fluid, let's say, or some liquid, let's say L. So rho L is 10 to power 3 kg per meter cube. Side of the cube is 10 centimeter, and the mass of the cube is 600 grams. So we have to find what is the amount of, what is the height of the body immersed inside the liquid. So that, let's say that height is some x. So we have to find x only. So how do we do that? So here two things are involved. First of all, this body is at rest in this whole liquid. That is, it is not moving at all. So this means that if we say there is some kind of upward force acting on this body, then that upward force should be balancing the downward force, which is the weight of this object. So this object has some weight W, which is balanced by the band force. And depending upon what weight of the object is, the X will adjust automatically. This is what we have to learn. Okay, what happens if there is an object which is immersed in a body? I increase the weight of the body. So naturally, we think that the body will sink even more inside the liquid. That's what happens, right? Let's say if you immerse some kind of, um, let's say if you immerse a empty bottle of cola in the water bucket, let's say in any kind of bucket you can take and immerse an empty bottle of cola. So it will simply float above water, as is the natural experience. And if you basically fill that cola bucket with, let's say, orange juice, or let's say with some color. Let's say you're preparing for some festival and you want to fill it with colors. So you fill the water bottle with some colored water, and when you have filled the water with color, definitely its weight will rise. And as its weight rises, it will sink deeper in the water. So this is what you can do. You can simply open the cap of the water and keep filling the color inside the water bottle. So automatically it will go inside the water bucket. Or alternatively, you can basically fill the whole water bucket with color. So what is X? Weight. The weight of the uh, cubical block is 600 grams. That is 600 into 10 to the power minus 3. So this is the uh, mass of the block which we are considering. Will multiply it with action to gravity. That is, this becomes weight of the body, mg. This will be equal to x into 10 uh, centimeter square. So that will be 10 square into 10 to the power minus 4 into density of the liquid 10 to the power 3. So 10 to the power 3 into 10 to the power 2 into 10 to the power minus 4. So basically this is the whole volume of the fluid which we are considering. This is the whole volume of the bodies which we are considering. This is the volume multiplied with 10 to the power 3. That is the density of the liquid into G. So this is the volume of the fluid displaced by the body. That is X into the area of the basically the cube. Area of the cube is this into height X into density of the liquid into G. So this is the buoyant force, which we said should be equal to the weight of the body. So I hope that is clear. So again, just to make it clear, this is basically area of the body. Area of the body into the height, which we are saying. Height of the body, which is immersed. So this becomes the total volume displaced. So this is the weight of the fluid displaced. This is the V rho G. So simply calculating this will become 6 is equal to X into 10 into G. So this is basically 6 by 100 meters or simply 6 centimeters. So this is the height with which the body, the cubical block will descend inside the water fluid. This is water basically, whose density is 10 to the power 3 uh, to balance the weight. Now there are other cases of using Archimedes principle as well. Uh, like one of the questions which comes is there are cases of two fluids, and in those two fluids we basically put an object inside it. So how the band force acts and things like that. So it's pretty interesting in that case how the band forces act. One of the other cases which we can take is that of a rod which is inclined inside a fluid. So for that we need some knowledge of torque as well. So one of the questions which comes is that of a body. So when we take a rod and we immerse it in a body of water. or body of a liquid, whatever liquid it could be. Let's say this is liquid of density rho L, and this rod it is kept like that. So question which is asked from us is, okay, if this rod of length L is, let's say, kept like this inside this rod, inside this water bucket, so what angle would this rod make with the vertical? So how is this rod basically resting here? So you can imagine a lot of ways. You can say that okay, this rod is something hinged. This rod is hinged at this point. And the angle which is making is theta, and density of the liquid is rho L. Whatever need quantities which you need, let's say we would need the length of the rod. So that we have taken already, that is L. Let's say we would need the cross-section area of the rod. So let's say the cross-section area of the rod is some S. And let's say the density of the rod is some rho uh, R. Density of the rod. S is cross-section area. So we know the cross-section area, we know the rod, and we have an interesting question in front of us. How is actually Archimedes principle acting here? So Archimedes principle says that okay, it is basically equal to the weight of the fluid displaced. That is the force acting on the body. Force is equal to weight of the fluid displaced. Here we also want to demonstrate okay, where this force acts. That is the point of the question. Every question, and basically we have to get some learning from it. Its application is secondary for us. We'll solve this question. But what we want to learn is that okay, where does this band force actually act? We know that in the previous case, simply the band force was balanced by the weight of the body. So it was pretty easy to get, right? We simply said that okay, the body is submerged, it is at rest, it is in equilibrium. So when it is in equilibrium, the band force simply equals the weight of the body. So there is no question okay, whether the band force is acting in some other line. It is able to tilt the body, it is able to displace the body or something like that. Some interesting thing happening. That was not that. It was simply an application of the formula which we learned. Here we want to see where it acts. So where do you think the band force will act here? Would it act at the center of the rod? We would naturally think that if this is the rod, if it were completely inverted in this immersed in this body, it would act here. But it's not like that. Basically, we must remember how the band force was generated. So we knew that the band force acts where the body was displacing the fluid, where the fluid was present. So the fluid had to be present here, in which the rod is there now. So if the center of fluid which we displace we consider, it is at that point the band force acts. That is the center of the rod, part of the rod which is immersed inside the fluid. So once more I will say it is at the center of the rod which is immersed inside the fluid. So only that part of the rod is immersed inside the fluid. At its center, the band force will act. So this band force, let's say, is FB. So that's it. Weight of the fluid would act at the center at some other point, let's say this some W. And we have pretty much done the question. That's it. So we'll say whatever is the length of the rod which is inside it, inside the fluid. So we'll say that particular rod, let's say length uh, is, let's say this angle is some theta and the length of the rod is L. So what can we say about the weight of the body? So W is weight. We'll say density of the rod rho R into length rod L into G. This is the net downward force acting on the body, and there would be a corresponding torque because of that, right? So if the angle which we are making here is some theta angle, right? Like this, the angle which we are making is some theta. So now we'll say, let's say, for the time being, let's say the fluid is filled up to the height h inside the rod, inside the bucket. So h uh, upon cos theta, this would be the length of the rod inserted inside the liquid. So h upon cos theta, this is particular length of the rod submerged. Okay, now so then we will say h by cos theta. From that only, that term only, we can derive all the other things like what is the volume. So h by cos theta into cross section. Then we can say what is the volume. So h by cos theta into s. This becomes the volume into density of the rod rho. So density of the rod we have given as rho r, or density of the fluid, because we want to say what is the band force. So rho L, fluid is a liquid, into G. So this is the band force. Band force has to be multiplied with the uh, point at which it is acting. Okay, we want to calculate the torque, right? There would be upward torque because of this band force. So this particular length is again h by cos theta. So h by cos theta by 2, that would be that particular length. And we would say, okay, what is basically this length? Basically, this is the length which we are talking about, this length. So what would this length be? We will say this length is h by cos theta, and its vertical component would be h by cos theta into sin theta. So it would be h tan theta. So h tan theta by 2 would be this length. Again, I'll say this is h by cos theta. This is h by cos theta by 2. H by cos theta by 2 into sin theta. That would be this length, h tan theta by 2. So this is the length which we are referring to. So we'll multiply this with h tan theta by 2. So multiplying this with equating this with density of the rod L and G won't give us anything, because again this is some force. Force will we have to multiply with the length to get the torque. So again this whole length is L, so this length would be L sin theta. So rho R L G L sin theta by 2. This is the length which we are referring to. So that's it. We have got our answer. So we have H into S, density of the liquid L, G, at least we can cancel, and 2 also we can cancel. So H, S, rho L, H again, so this is h square tan theta by cos theta. So this is sin theta divided by cos square theta is equal. So from h by L, we can, I think, or we can, if we know h and L, we can find cos square theta. So that's it. That's what we were looking for. This implies cos square theta or h by L whole square into s into rho L. Here we will also have one s. So s and s cancel. That is rho r equal to cos square theta. So cos theta is equal to h by L square root rho L by rho r. So this is the angle which you are looking for. So thank you for joining.